Hello everybody. I'm going to be looking at the general concept and implementation of pipelining in a MIPS processor. Now we have previously learned about the architecture and uses of a single cycle and multi-cycle MIPS processor, but we kind of shortchange much of the hardware if we keep the process exactly as it currently is, because the processor doesn't actually use most of the hardware if we handle instructions one by one. Because of this large inefficiency of the use of the hardware available, the concept of pipelining was introduced to take advantage of the hardware by initializing the next instruction before the previous one is fully complete. So how exactly does pipelining work? It's easy to think of pipelining in the way we think of doing any activity in our daily lives. Now pretend that it's the weekend and you have 4 massive loads of laundry to do. Let's also pretend that you have a big test for your computer architecture class and you can't devote your whole evening to doing laundry. Now this is how one might initially approach doing all these 4 loads. Well, this is all fine and dandy except for one problem. It takes 6 hours to do all 4 loads, from start to finish, doing it this way. This is exactly the way we have been using our processors in this class so far. Not exactly efficient. Now let's look at the second step in our process here. After we have done a wash, we put the load in the dryer and wait for the dryer to finish the load. But just standing there at the laundromat staring into space isn't exactly the best use of our time. So what if, instead of staring blankly, we can get ahead on the next load while this previous one finishes? After all, we're free and the washer's free. So we put the next load in the washer as soon as we finish putting the previous one in the dryer. Now we have both the washer and the dryer going while it does 2 consecutive loads. Let's assume that both the washer and the dryer take the same time to wash and dry a load, such as they're done at the same time and I can move to the next step in each respective cycle. This means that once I move the second load to the dryer and the first load to the folding table, the washer is once again free to use. And once again we pack the washer with more clothes to start our third load. Now, instead of waiting for the dryer and washer to finish, we can fold the clothes from the first load. As you can see, we are kind of stacking one load on top of the other and having this entire process run in parallel. And it certainly pays off because instead of sitting around boring ourselves to tears waiting for washing and drying cycles to finish until 2 a.m., like we're doing here, under this way, we're constantly doing multiple things at once and finishing the same amount of loads by 9:30 p.m. This is the same way that pipelining works in a MIPS processor. Instead of all this stuff with washing and drying clothes, let's replace the steps of this laundry business with each step in the MIPS processor. Each instruction in a MIPS processor has 5 different steps: instruction fetch, instruction decode and register fetch, an execution step where we carry out a variety of different operations like R-type instruction execution, memory read and write address computation, and branch completion or jump completion if we're doing branches or jumps. Then there's a 4th step where we carry out everything having to do with memory, such as memory read address or memory write completion. If we're also doing an R-type instruction, this is a step where that instruction is completed. The 5th step, write back, is the final one, which also doubles as memory read completion in the case of some instructions involving reading memory. So these are all the 5 steps of doing a single instruction. Now, when we have multiple MIPS instructions in a program, the processor can start doing the next instruction before the previous one is complete in order to maximize efficiency in our application. Notice that when stacking each of these instructions together, we have to move the steps of the second instruction 1 cycle after the first, the steps of the third instruction 1 cycle after the second, and so on. After all, we can't exactly put a washer and dryer to work on 2 loads at once, much like we can't make an ALU do 2 different operations at once. So now that we have everything to get pipelining going, do we need to change anything in the pipeline data path itself? The answer is yes, but we don't really have to change much. Now, data path needs some way to be able to help with each step it's in. In addition, we need to be able to kind of stop, or rather isolate, each step in a data path since we're going to be using the same path for multiple different instructions. To accommodate this, we need to introduce state registers. These registers serve as kind of a partition that separate each of the 5 steps of an instruction such that we can make this conga line of instruction steps work. We'll name each of these state registers by the 2 steps that they're separating. For instance, we'll name the first partition ifetch/dec to indicate that this will separate instruction fetch and decode. The second is named dec/exec to indicate that this separates decode and execution, and so forth. Something else that we need to be able to move between each of these partitions are all the control signals that we'll need for each individual instruction. Now, we're reading these control signals in the instruction decode step, but once we move the instruction past that decode step, we need to be able to read the control signals for the next, and thus we can't keep them there while the previous instruction is finishing its thing. Because we need to keep this process moving, we're going to have to save these control signals in the state registers, such that one whole data path can remember multiple control signals for different instructions. Note that the further we go along the path, we get rid of the control signals we know we're not going to need anymore moving forward. Now, remember when we were deciding why MIPS was easier to work with in the beginning of the course, as in all the instructions have the same length? Well, this advantage certainly comes handy when we're working with pipelining, because we don't have to worry about varying instruction lengths when we're trying to cram multiple instructions into one data path. We can easily and neatly fit the instructions between stages, even as we fetch and decode them without having to worry about this. It's not all rainbows and roses though, because pipelining also comes with its fair share of issues. Pipelining can introduce multiple problems. A big one, what we called hazards. Hazards are issues that pop up when we're doing multiple instructions at once. Now, you might think that on a data path level we've tried to make it as painless as possible by introducing all of these state registers and saving important control signals in these registers, but there are problems that occur outside of the scope of the data path level. There are three main hazards that we're briefly going just to look at in this video, and they are structural hazards, data hazards, and control hazards. Structural hazards occur when two different instructions try to use the same resource at the same time. If you remember, we originally tried to mitigate this issue by starting at an instruction one cycle after the other. But this is not enough. If we stack enough instructions of certain types, we can come up with a combination where two instructions that are multiple lines apart try to use the same resource, which can present plenty of problems on its own. The second type of hazard is a data hazard. This one is simple to understand. Let's take a look at this pair of instructions that are meant to be done consecutively. You might be surprised that if we implement the pipeline process exactly as we have it now without any hazard control, just these two instructions will present problems. Do you see why? Let's take a look at the output of this instruction. Now, let's take a look at the input of the next instruction. If we look at the instruction steps, we can notice the problem right away. We don't store the result of this instruction in its respective register until the last step. But in the second instruction, we read the same register in the second step. This means that if we do this addition in the first instruction, it won't be saved in the registry in time for the second instruction to actually get the updated value when it reads it. Again, this is what is called a data hazard. The third instruction is known as a control hazard, which works a little bit like the way the data hazard works. For instructions like exceptions, branches, and jumps, it takes some time for the data path to properly compute the applicable comparisons and new destinations of the program before we're ready to move the program in that direction. However, if we continue to stack the program in the same way and pretend like we're not changing our course in the program might start doing operations that we're not meant to be doing at all. If, for example, we have a branch instruction that could potentially skip the next two instructions as per the branch conditions, and we stack these next two instructions just to get ahead in the pipeline is effectively deciding to not take the branch regardless of what the conditions already are. This presents a problem if we were actually going to skip these next instructions. These are the problems presented as a control hazard. There are multiple ways of solving these hazards, a simple one being rather specific. If we look at these two examples, we see that there is a potential hazard when we're doing a register read and a register write at the same time. But note that in the data path, it is actually possible for us on a hardware level to both read and write to the register during the same cycle. Because of this, we can modify the way the register read and write works by dividing this register into two, using the positive and negative edges of the clock. If we write to the register on the negative edge and read from the register on the positive edge, we can even write to and read from the same register using two different instructions without missing a beat. But what if the instructions are side by side? A more general way of solving data hazards is doing what is called stalling. sometimes known as inserting bubbles. Since in some cases we absolutely cannot get the appropriate, most up-to-date information from a register, sometimes the best course of action is simply to stop the stacking process by stalling the program so that we can let the register values catch up. We can see how it works here, where stalling the program allows for this instruction to get the right register value when it needs it. But let's look at this instance here, where everything needs to be stalled. This is highly inefficient, because we're basically back to not even doing any pipelining at all because we're stalling the program so much. But let's think about this for a second. Look at the way that this instruction works. Notice how in the last two steps there is no way for this register to change its value? The thing that matters most to this instruction, which is the register value, has already been computed by this time. So why do we need to wait until here for us to be able to fetch the register value if the register value is ready right here? Well, we don't, which is why we can take the data that comes out of this step and stick it right into this step in this other instruction, such that the program doesn't have to sit around waiting for no reason. This is what is called data forwarding, and as you can see, we don't have to stall the program to oblivion and keep the pipelining advantages at the same time. Now, each of these hazards are more complicated than this, and properly implementing the control solutions to this is more involved, but that's outside the scope of this video. With this video, we have gone over what is pipelining, a basic way of implementing it, what are some issues when we implement it, and how to solve these issues in a general manner. I hope you have learned something from this, and thank you for watching.